All right, so we're really diving deep into AI image generators today with this paper on diffusion models.
Yeah.
And I got to say, I'm kind of stuck on this question of how they work so well.
Right.
Like, it's one thing to train an AI on tons of data,
Sure.
but these diffusion models, they start with pure digital noise.
Yeah.
And then, bam, suddenly we have these crazy realistic cat pictures.
It is pretty wild when you think about it.
It really is. So how does that even work?
Well, it all comes down to this idea of representing complex information effectively.
Okay, say more about that.
So in computer science, we have this concept called the curse of dimensionality.
Curse of dimensionality.
Yeah, basically it means that the more complex something is, the more data you need to represent it accurately.
Interesting. So, like, the more detail something has, the harder it is to, like, describe it perfectly?
Exactly. And images, well, they have a ton of detail.
Yeah, no kidding.
So you would think you'd need an insane amount of data to create realistic images from scratch.
Right. It'd be like trying to bake a cake, but needing to understand every single atom in every single ingredient first.
Yeah, kind of like that.
So how are these diffusion models getting around this curse of dimensionality thing?
Well, instead of trying to build an image piece by piece, they do something really clever.
What's that?
They start with that digital noise you mentioned, and then they train the AI to gradually remove it until a coherent image emerges.
So instead of like painting a picture, they're more like sculpting it, chipping away at the noise until they find the image hidden inside.
That's a great way to put it.
So they call this denoising.
Exactly.
And somehow this denoising process leads to these incredibly realistic images.
It does. And what's even more interesting is that the paper shows these models aren't just memorizing the images they're trained on.
Wait, really?
Yeah, there's actually a point where they transition from photographic memory to actual generalization.
Hold on. So you're telling me there's a tipping point where these AI models go from spitting back what they've seen to actually understanding something about images?
It seems that way.
Okay, now you have to tell me more about that.
So the researchers, they tested this by training separate models on totally different sets of images.
Different models, different images. Okay.
And what really blew their minds was that with enough data, these models started producing almost identical images.
No way.
Yeah, even though they had never seen the same examples.
So it's like these AIs were learning different visual languages, but somehow they ended up speaking the same language in the end. That's wild.
It is, and figure 2 in the paper actually shows this really well.
Okay, what is your?
So with a small data set, the output looks a lot like the training images, almost like simple copying.
Right.
But as the data set grows, the outputs become more unique and yet eerily similar across models trained on that different data.
So it's like they're tapping into some like hidden structure of images.
Yeah, like some visual code that exists beyond any specific example.
That's kind of spooky, actually.
It is a bit. And the researchers found this to be true across the board, too.
Really?
Yeah, different data sets, different architectures. It didn't matter.
Wow. So this wasn't just some fluke. This is like a fundamental thing with these diffusion models.
It seems that way.
Okay, so I'm on board with this idea that they're not just memorizing.
Okay.
But if they're actually learning, how are they doing it?
Right. So the paper gets into the nitty-gritty of this, and they talk about something called a geometry adaptive harmonic basis.
Oh, what?
A geometry adaptive harmonic basis, or GAHB for short.
Okay, that sounds complicated.
It is a bit, but it's actually a really elegant concept.
Right, I'm listening.
So think about trying to describe a complex shape like a wave.
Okay, like a wave in the ocean.
Yeah, exactly. It's much easier if you can break it down into simpler repeating patterns, right?
Sure, that makes sense.
Well, that's basically what these models are doing with images.
Instead of describing every single pixel, they're finding these underlying patterns that make up the whole picture.
They represent images as combinations of these oscillating patterns, kind of like sound waves, but for shapes and edges instead of sound.
Okay, so they're like analyzing the image in terms of its visual frequencies.
Yeah.
And this helps them with the whole denoising thing. How?
Well, imagine you have a photo with a bunch of static over it.
Okay.
The model uses these harmonic patterns, these GAHBs, to analyze the image.
Right.
It figures out which parts are the actual image content and which parts are just that visual noise.
Okay.
And then it emphasizes the important patterns, those harmonic building blocks, and discards the noise like turning down the static on a radio.
So it's like they're shrinking the importance of some of those harmonic patterns while boosting others.
Precisely.
And all in the service of cleaning up the image.
Exactly. And this method of picking out the essential patterns, it turns out to be incredibly efficient for representing images.
Interesting. So it's not just about making the images look good, it's also about finding the most efficient way to represent the information.
Exactly. It's
Yeah.
similar to how JPEGs work, actually.
Oh yeah, how so?
Well, JPEGs compress images by focusing on key frequency information and tossing out less important details.
Right, so these diffusion models are kind of doing something similar, but on a much more sophisticated level.
Exactly. They're learning to see the world through this lens of geometry adaptive harmonic patterns.
It's like they've developed their own visual language, and the more they learn, the more fluent they become.
That's a great way to put it. And the researchers actually found some pretty compelling evidence to support this whole GHB thing being central to how diffusion models work.
Oh, really?
Yeah, they did this really clever experiment.
Okay, I'm intrigued. Tell me more.
They created these synthetic images where they knew exactly what the optimal basis should be.
Okay, so they like rigged the game to see if the model would figure it out on its own.
Exactly. And the result was amazing.
What happened?
The model learned incredibly similar representations when trained on these synthetic images.
Even though it had never seen them before.
It's like it was able to solve the puzzle without ever seeing the picture on the box.
So they basically confirmed that the model wasn't cheating, it was genuinely figuring out these efficient representations on its own.
Precisely. And figure 4 in the paper shows this beautifully.
Okay, what does it look like?
Well, you see these synthetic images, which honestly look kind of like abstract art at first glance.
Right.
But then right next to them, you see the model's learned representations, and they're these really elegant oscillating patterns that capture the image's structure perfectly.
Wow. So it's like watching the model unlock a hidden code.
It really is.
Okay, you've convinced me this whole GAHB thing is clearly a big deal.
It's pretty remarkable.
But here's a thought. What happens when you throw an image at it that can't be easily broken down into these neat harmonic patterns?
That is the million-dollar question.
Like, what about images that are more abstract or chaotic, where there aren't those obvious edges and patterns to latch onto?
Right, and that's actually one of the things they explored in the paper.
Oh, really? So what did they find?
Well, they found that when they trained the model on images that don't naturally lend themselves to those GHBs, the model's performance took a hit.
Interesting. So it's like the model is so used to seeing the world through those harmonic glasses that it struggles to adapt when something doesn't quite fit.
Exactly. It's like trying to fit a square peg into a round hole.
Right, because the model is so good at finding these efficient harmonic representations, it tries to force fit them onto everything, even when it's not the best approach.
Precisely. And they actually did a really interesting experiment with images of simple disks.
Discs.
Yeah, just plain circles. And what they found was fascinating.
What happened?
Even though a much simpler representation would have been ideal, the model still tried to impose those GAHBs.
So even with something as basic as a circle, the model was so stuck in its ways that it couldn't see a simpler solution.
It's like it got so used to finding its harmonic hammer that everything started to look like a nail.
And did that actually impact its performance?
It did. You can actually see in Figure 5 how the model's performance suffers because it's so fixated on those harmonic representations.
Huh. So even these incredibly powerful AI models have their quirks and biases.
It seems that way.
It's strangely human, isn't it?
What do you mean?
Well, this tendency to stick with what we know, even when it might not be the best way to see the whole picture.
That's a really interesting point.
So if the model struggles with something as simple as a disk, what happens when you throw even weirder images at it?
Well, they tested that too.
Oh, how?
They did this experiment with what they called shuffled faces.
Shuffled faces. So like taking a normal picture of a face and then just like scrambling all the pixels.
Exactly. And because these shuffled images lack any kind of spatial organization, the model really struggled.
Because it was expecting to find those harmonic patterns based on like how a face is usually structured.
Precisely when you disrupt that completely, it throws the model for a loop.
You know, it's kind of comforting to know that even with all their power, these AI models still have limitations.
I can see why I'd say that.
It makes them feel a bit less like magic and a bit more understandable.
That's a good point. And, you know, this whole discussion about GHB limitations and biases, it actually opens up even bigger questions about these models and how they see the world.
This is where it gets really interesting. Tell me more. So it's like we're seeing these cracks in the facade, these hints that these AI models, as impressive as they are, might be seeing the world through a very different lens than we do.
It really makes you wonder if their whole world is built on these harmonic patterns, these GAHBs, how much can they really understand about an image?
Right, like they might be getting the building blocks, but not the bigger picture.
Exactly. It's like they're looking at a painting and only seeing the brushstrokes, the colors, the textures, but not quite grasping the story. Those elements tell the emotions they evoke.
Okay, now that's a really interesting way to think about it.
And that leads us to a pretty big question. How well can these models really handle the chaos of the real world?
Right, because the real world doesn't always play by these neat harmonic rules.
Exactly. So what happens when they encounter something truly unique, something that falls outside those harmonic boxes they love so much?
Yeah, they can try to hammer it into a harmonic box, even if it doesn't belong.
It's definitely a possibility. And, this isn't just about generating cool images anymore.
Right, the stakes are a lot higher than that.
Exactly. This has implications for everything from self-driving cars, navigating unpredictable streets, to AI diagnosing diseases from complex medical scans.
Whoa, so we're talking about AI making really important decisions that could have real-world consequences.
Precisely. And if these models have these built-in biases, these tendencies to see the world through these very specific harmonic lenses, we need to understand those limitations.
Especially if we're going to trust AI to make those decisions.
Exactly. It's all about understanding the strengths and weaknesses of these models so we can use them safely and effectively.
Absolutely. Well, this has been a really eye-opening deep dive.
I agree. It's amazing how much there is to learn about these AI models and how they work.
We started off wanting to figure out how AI image generators work. And now we're grappling with these huge questions about the nature of AI itself.
It's a rapidly evolving field, and it seems like every answer just unlocks a dozen new questions.
And that's what makes it so exciting.
It definitely keeps things interesting.
Well, you heard it here first, folks. What started as a deep dive into AI image generation has turned into a profound exploration of how these models see the world and the implications of that for the future of AI.
And who knows, maybe by understanding these models, we might even learn something new about how we perceive the world.
Now, that's a thought-provoking note to end on. Thanks for joining us for this deep dive.
It was my pleasure.
Until next time, keep those questions coming and keep exploring the ever-evolving world of AI. Ever mess around with those AI image generators?
Type in something totally out there.
Like a cat riding a unicorn through a rainbow tornado.
Yeah.
And it just makes a picture.
Right.
It's crazy.
It's wild.
The stuff they come up with looks like it could be in a gallery.
I know.
But the how is kind of like magic to me.
Like something only these AI wizards really get.
What if we could break down that magic a bit today?
That's exactly what we're doing today.
We're going to unpack how these AI image generators work.
Specifically, something called diffusion models.
Okay.
They can take pure noise and turn it into
stunning and original art.
Original. That's the thing.
You got to wonder.
Are these AIs actually artistic geniuses?
Or are they just really good at copying and pasting?
Yeah.
Because they're trained on tons of images, right?
Millions and millions of images.
That's where this research paper comes in.
This is what we're diving into today.
Okay.
It looks at this big question in AI.
How do we know these models are actually learning?
How do we know they're generalizing?
Not just spitting back something they've already seen.
Right, because you could train an AI on
a massive data set of just cat pictures.
And it might just memorize every single one.
Right.
But that wouldn't be true learning.
Totally.
And it wouldn't be that useful.
Or actually making something new.
So how did the researchers figure out if these AI models
were just
sophisticated copycats?
Or if they were really learning something fundamental about how to create.
So they split their training data,
which is just a massive amount of pictures,
into two completely separate data sets.
Yep.
They trained separate diffusion models.
One on each data set.
And the question was,
would these two models,
having never seen the same images,
still be able to create similar outputs?
So it's like if we both looked at
a bunch of pictures of cats.
Okay.
But different pictures of cats.
Yeah.
And we both try to draw a cat from memory.
If our drawings look alike,
it would suggest that we both learned something about
concept of catness.
Exactly.
And that's exactly what they found
Wow.
with the diffusion models.
Once they're trained on a big enough data set.
The outputs from the two models were really similar.
Wow.
Even though they were trained on completely different images.
That's really cool.
So that's pretty strong evidence
that these AI models aren't just memorizing.
They're learning some general rules about what makes an image look a certain way.
But how are they doing it?
This is where it gets really interesting.
And where this idea of geometry adaptive harmonic bases comes in?
Or GAHBs.
GAHBs.
All right, you're going to have to break that one down for me.
Yeah, it sounds intimidating.
But it's actually pretty intuitive.
Okay.
Once you wrap your head around it.
Imagine you're looking at a picture.
Okay.
Now imagine breaking that picture down.
Into its most basic visual components.
Kind of like a mosaic.
Each piece of the mosaic represents
the different pattern or element of the image.
I'm with you.
GAHBs are like those mosaic tiles.
Okay.
But with a special ability.
Okay, I'm picturing a mosaic now.
But with magic tiles.
What's so special about them?
These GAHBs, these tiles, they can actually change
their shape and size
to best fit the content of the image.
Instead of being stuck with those same size squares,
your mosaic tiles can morph.
They can adapt
to perfectly capture the curves of a cat's ear.
Or the sharp edges of a building.
So it's like a mosaic that's custom fit to each picture.
I'm starting to see why you called it intuitive.
But how does this help the AI actually make images from noise?
Well, the researchers found that when these diffusion models are doing their thing,
gradually denoising that random starting point
to create a recognizable image, they seem to be naturally drawn
to representing the images
using these GAHB-like structures.
So these diffusion models,
they really like GAHB.
These adaptable mosaic tiles
that can represent the world in a way that makes sense to them.
Yeah.
But is there something special about, like,
how they use them?
Can we actually see these GAHBs in action?
That's the cool part.
The researchers didn't just, like, theorize about GHBs.
They actually designed these experiments to see.
If that's really what the models were using.
Oh, wow.
They used a special type of image called K-images.
And
so
you don't need to be a mathematician to get this.
Okay, good.
Basically, these images have, like,
a specific kind of smoothness
that the researchers could control.
So it's like having a dial.
That lets you adjust how smooth or detailed an image is.
Exactly.
Think of turning the dial up.
For like super smooth, almost blurry images.
And then down for those with lots of detail.
Okay.
And by training the diffusion model
on these K images
with that, like, smoothness is dialed to different levels,
they could see if the model's approach changed. And did it?
It did.
The amazing thing was, when trained on these Kadkhodaie images,
the diffusion model naturally gravitated
towards using a GAHB-like approach
to denoise them.
Wow.
It's almost as if the model, like, instinctively understood
GAHBs were the best way
to represent and recreate
these kinds of images.
So it's not like the researchers were like, hey, use these GIGB things.
It figured it out on its own.
Exactly.
That's wild.
It's kind of like giving someone a bunch of Legos.
And they're not just building random towers.
They're like figuring out architecture.
Right.
And the results speak for themselves.
The model achieved near-perfect denoising.
With those cannages?
When it used this GAHB approach.
Wow.
It really shows how powerful this is for AI image generation.
So we've gone from
AI image generators are magic.
It's just
all about GAHBs.
But you know what they say?
Too much of a good thing can be bad.
Are there times
when this GAHB approach,
elegant as it is,
isn't the best tool for the job?
You're thinking like a true deep diver.
And you're right.
There are always exceptions.
Remember how we talked about how the researchers...
They were interested in how well the AI could generalize.
Yeah.
Well, they wanted to see what happened.
When the AI encountered images
that are very similar to each other.
Like a million pictures of the same thing.
Exactly.
They experimented with images.
On something called low-dimensional manifolds.
Imagine you have a coffee mug.
And you take a bunch of pictures of it.
Okay.
You rotate it a little between each picture.
So each one's a bit different.
But it's still clearly the same mug.
That's a low-dimensional manifold.
A collection of very similar things.
Okay, I'm picturing
a whole gallery wall of slightly different coffee mug photos.
So what happens when you
unleash the AI on that?
Well, logically,
you wouldn't need a super complex approach
to denoise those images.
Even a simpler method could probably handle it.
Right.
But
here's where it gets interesting.
Even in those cases,
where a simpler approach would have been more efficient,
the model still clung to its GAHBs. At least partially.
So even though it had...
like a perfectly good hammer.
It insisted on using its...
fancy multi-tool.
Even if it was more complicated.
Yeah, you got it.
That shows something really important about these models.
They can do amazing things.
Generating realistic pictures.
Learning general principles.
But they also have these inherent biases.
These tendencies that might lead them down a more complex path.
So it's not just like a straight line from noise to a masterpiece.
These AI models,
They have their quirks,
yeah,
their preferences.
even like their favorite tools,
Right.
like those GAHBs.
It makes you think, though.
What's the bigger picture here
Why should we even care?
about how these AIs are making art?
That's a great question.
Especially if they're still figuring things out themselves, right?
Right.
I think the answer is in the potential
Like, we've uncovered this.
fundamental principle.
That seems to be driving.
How these AIs learn to see.
And then recreate the world.
Okay.
That's huge.
I'm with you. We've peeked behind the curtain.
Learn some of the AI secrets.
But how does that translate into something real?
Imagine this.
What if we could use this knowledge about GAHBs
To design even more powerful AI models.
Yeah.
Models that can generate,
not just pictures,
but like 3D worlds, lifelike animations.
entire virtual universes that feel as real as this.
Okay, now you're speaking my language.
AIs that could design video games.
Right.
Or even help architects and engineers visualize their designs.
Exactly.
That's amazing.
And that's just the beginning.
We've been talking about how these AIs use GAHBs to understand images right.
Yeah.
It makes you wonder
Could this be a clue?
to how our own brains process visual information
You're saying
by studying these AI models.
we might learn something about how we see the world.
It's possible.
That's incredible.
It really is.
It's like we set out to make artificial intelligence.
And we might find
The secrets of our own intelligence.
that's a great place to leave.
I gotta say.
We started talking about AI art.
And we ended up talking about the nature of intelligence.
It's pretty wild.
It is fascinating.
Until next time, folks,
Keep exploring and keep asking questions.
who knows what you'll discover? All right, so get this right. Today, we are diving into AI image generation,
Okay, yeah.
specifically these diffusion models
Right.
that can create like photorealistic images
Yeah.
out of thin air.
Basically from scratch.
From scratch, you give them a few lines of code and bam,
Yeah.
you've got a masterpiece.
Yeah.
But here's the thing that always kind of blows my mind.
Mm-hmm.
How do these AI models learn?
Yeah. How do they learn to be so creative
Yeah.
without just spitting out copies of the images they were trained on, right?
Yeah.
It's like, are they really artistic geniuses or are they just really good at mimicking?
It's like, are they really understanding what they're seeing?
Right.
Or are they just good at like, kind of.
Well, it's a question that's haunted researchers.
Yes.
For quite a while now, you see. One of the biggest hurdles in AI has been this whole issue of memorization versus generalization.
Oh, interesting.
So think of that student, right?
Yeah.
Who crams for a test,
Right.
but forgets everything the next day.
Yeah. Yeah. We've all been there.
We don't want our AI to be just a cramming student.
Right. We want them to actually learn.
Exactly. We want it to understand.
Yeah.
And learn from the data, not just memorize.
Absolutely. So how do we make sure our AI is graduating with honors?
Right.
What's going on in those digital brains?
Well, imagine, trying to make sense of data, not in our usual 3 dimensions, but in hundreds, thousands
Of
dimensions.
many
And it's like trying to find a needle in the most massive haystack you've ever seen. That's the world that these AI models are grappling with.
Wow.
And it's a recipe for what we call the curse of dimensionality.
The curse of dimensionality.
It's tough.
Okay, so lost in a sea of data, no wonder AI tries to take shortcuts.
Right.
By memorizing, can't you really blame them?
Right.
But doesn't that mean they're stuck?
Right.
Just regurgitating what they've already seen.
So here's where things get really interesting with these diffusion models, this research paper that we're diving into.
Okay.
It actually found that when you train these models on a massive, massive amount of data,
Okay.
they can actually break free from that memorization trap.
Right.
They actually start to generalize.
Wow.
They even found that 2 models trained on totally different sets of images
Okay.
could generate almost identical pictures.
Wait, hold on, back up. So if we show these 2 AIs 2 completely different photo albums,
Completely different data sets.
they could still both like imagine or create the same, like let's say a cat wearing a monocle.
Right.
That's wild. How is that even
This
possible?
million-dollar question.
Yeah.
And it points to these really powerful inductive biases at play within the model.
Inductive biases. Okay, break that down for me. What is an inductive bias in this context?
So it's like these biases. They give the AI a set of rules of thumb about how the world works,
Okay.
even if it hasn't seen every possible example.
Gotcha.
Like imagine, teaching two artists
Yeah.
the same rules for perspective and color theory.
Okay.
They might paint different scenes,
Yeah.
but their work will still have this shared visual language.
Ah, okay, okay. So it's like a shared understanding
Right.
of how things work visually.
Exactly.
Gotcha, gotcha. So are these biases like the secret sauce behind how these diffusion models create these mind-blowing images?
You could say that, yeah. And the paper really dives into one specific bias
Okay.
called geometry adaptive harmonic bases.
Geometry adaptive
GAHBs for short.
GHB, sorry. We're already knee-deep in this deep dive.
Right.
Tell me more about these GAHBs. What are they and how do they work?
Well, you can think of GAHBs, right, like building blocks for images.
Okay.
But instead of simple pixels, right, they're more like sophisticated brush strokes that capture both the smooth areas and the sharp edges in a really efficient way.
Interesting. Okay, so GHBs are like a painter's secret weapon.
Yeah.
Giving them the perfect brushstroke.
Yes.
To capture every little detail.
Exactly.
But how do these AI models even know about GHBs in the first place? Did someone, like, teach them about these special building blocks?
That's the incredible part. It's not that we explicitly programmed the AI to use GAHBs.
Interesting.
The research suggests that deep neural networks, or DNNs for short,
DNN, okay.
which are like the brains behind these diffusion models,
Okay.
are naturally drawn to representing images using this approach.
Wow. So it's like they stumbled upon this fundamental truth
Yeah,
about visual information all on their own.
kind of.
It's amazing. But how can we be sure? Like, how do we know for certain that they're actually using GAHBs?
So to test this,
Okay.
the researchers, they devised a really clever experiment. They trained these DNNs on these special images where they already knew that the absolute best way to represent them mathematically was using something very similar to GAHBs.
Interesting.
Think of it like a controlled experiment, right?
Okay.
Where we know the answer beforehand.
Okay, so it's like giving the AI a pop quiz
Right.
and seeing if they naturally gravitate towards using GAHBs to ace it.
Exactly.
What happened? Did they pass the test?
They aced it. The DNNs consistently gravitated towards using GAHB-like representations.
Wow.
Proving that they have this inherent bias towards seeing and processing images in this particular way.
So we've got these AI models powered by DNNs that have basically taught themselves the secret language of images, GHBs.
Yeah.
And it's this understanding that allows them to create those incredible photorealistic images from scratch.
It's pretty amazing.
But you know what they say? With great power,
Yeah.
there's always a catch.
Always a catch, right?
What's the limitation of this whole GHB situation?
Well, you're right to be skeptical because while this discovery about GHBs is really exciting,
Yeah.
it's just as important to understand where these inherent biases might fall short. If we want to push AI even further,
Okay.
we need to know its limits.
All right, so what's the catch? What don't these GHBs quite capture?
Well, think about it. GAHBs are fantastic at representing things we see in the real world.
Okay.
Faces, objects, landscapes, things with smooth curves and defined edges.
Yep.
But what about more abstract concepts, things
Yeah.
that don't fit neatly into those categories?
You mean like abstract art? Like
Yeah.
if we asked our AI to paint something inspired by Picasso, it might struggle?
Exactly. To test this, the researchers did another experiment,
Okay.
but this time using very simple shapes. Just disks.
Discus, okay.
Now, the most efficient way to represent a disk mathematically is different from how you'd represent a face or a landscape.
So we're changing the rules of the game. It's not about curves and edges anymore. It's about understanding these more basic geometric shapes.
Right.
Okay.
And what's interesting is that even though a different approach would have been more efficient,
Okay.
those DNNs with their inherent bias towards GAHBs
Yeah.
still tried to apply that framework to the disks.
They really love those GHBs, huh?
Yeah, they do.
Talk about sticking to your comfort zone.
Right.
So did sticking to their GHB comfort zone pay off? How did they do?
Well, they didn't completely fail, but their performance wasn't as impressive.
Yeah.
And that tells us something very important about the potential and the limitations of these biases.
Okay, now I'm really intrigued. What does this all mean for the future of AI?
Yeah.
Let's unpack that in part 3. All right, so we've gone like really deep into these GAHBs,
Yeah.
these building blocks of images that AI seems to like really love.
Right.
But why should we care? What's the big takeaway for, someone like me, someone who's just trying to understand this whole AI world a little better?
Well, what's really fascinating here is that it gives us like a whole new way to think about designing AI.
Okay.
It's like we've discovered that our current AI, it's really good at understanding the visual world because of this inherent bias towards GAHBs.
Okay.
But what if we could design AI with different biases?
Yeah.
Right, biases that make them excel at things that aren't just about recognizing patterns and images.
Okay, so instead of just recognizing a cat in a photo, we could have AI that understands the concept of catness
Exactly.
on a whole other level.
On a deeper level.
That's pretty wild.
Yeah.
What would that even look like?
So it opens up some really, really exciting possibilities, right?
Yeah.
Imagine AI that's not just limited to mimicking the world it sees,
Right.
but can actually come up with completely new ideas.
Wow.
We could have AI composing symphonies that break all the traditional rules of music, or designing buildings that are both functional but also incredibly innovative.
So we could go from AI that paints like a master forger to AI that's like the next Picasso. That's a game changer. But how do we even begin to change these biases? It's not like we can just, swap out GHBs for something else.
Right. It's definitely more complex than just a simple swap.
Right.
But by understanding how these biases emerge, right,
Yeah.
from the structure of DNNs and the data they're trained on,
Okay.
we can start to nudge them in different directions.
Okay.
We could,
Okay.
experiment with different architectures for these networks.
Right.
Or explore ways to train them on data that represents abstract concepts more effectively.
So it's like we're giving AI the tools to think outside the box.
Yeah.
To move beyond just mimicking it into the realm of true creativity and innovation.
Exactly.
It's pretty mind-blowing.
And that's the beauty of this kind of research.
Yeah.
We start by trying to understand something very specific, right?
Right.
Like how AI generates images.
Yeah.
And we end up uncovering these fundamental insights about the nature of intelligence itself.
We've gone from digital art to the future of intelligence, all thanks to a bunch of pixels and some really clever algorithms.
These are pretty amazing.
Who knew a deep dive could take us so far?
Right.
And on that note, I want to leave our listeners with something to ponder. If our current AI is so good at, replicating the visual world because of GAHBs,
Yeah.
what other hidden structures, what other building blocks of knowledge might be out there?
That's a great question.
What we discover next that will unlock even more amazing capabilities of AI.
It's an exciting time to be thinking about these things.
Absolutely. Until next time, keep those minds curious.
Keep asking questions.
And we'll see you on our next deep dive.
All right, so you're scrolling through your feed, right? And you see another one of those crazy good AI images, the kind that makes you do a double take. Ever wonder how those things go from lines of code to almost like a real painting?
Yeah, it's pretty wild, isn't it?
It really is. And that's what today's deep dive is all about. We're getting into the guts of a research paper about diffusion models. Those AI artists everyone's buzzing about.
Right.
We're going to try to unpack how they actually, do that.
It's a really fascinating field, and it's changing so fast.
Yeah.
I think what we're really going to dig into today is how these models actually learn.
Yeah.
And what's so cool is by understanding that process, we can start to see what AI creativity really means, both the potential and maybe some of the limitations.
For sure, for sure. So the paper we're looking at is called Generalization in Diffusion Models Arises from Geometry Adaptive Harmonic Representations.
Catchy, right?
Super catchy. Yeah, we'll unpack that title, I promise. But basically, these researchers, they put these AI artists through their paces, right? They train them on tons of pictures of faces.
Yeah.
And here's the kicker. They used separate models and gave them each different images to learn from.
Yeah, so it's imagine a classroom full of art students, and they're all studying portraits, but each student gets a slightly different set of portraits to work with.
I like that. Okay.
So when they only had a few examples to go on, the models, they kind of acted like copycats.
Oh.
They could spit back pretty similar images to what they were trained on, but nothing too impressive. They were just memorizing the specifics.
Right, like tracing.
Yeah, exactly.
So then they decided to crank things up a notch, right?
Yeah.
They gave these models way more images, thousands more, to learn from. It's like they let those art students loose in a museum full of portraits.
Exactly. And here's where it gets really cool. With all those extra images, the models started to create totally new faces. Ones that weren't just copies of what they'd seen before. The researchers called this the generalization phase.
Interesting.
Like those art students, after seeing so many different faces, they started to understand, like, the essence of what makes a face a face. They weren't just copying anymore. They were, like, actually understanding.
Oh, wow, that's cool. So they went from copycats to, like, real creators
Right.
just by having more to work with.
Exactly.
But here's the mind-blowing part. Even though those models all learned from different images, as they got more data, their creations started looking more similar. It's like they were all arriving at the same understanding of faceness, even though they hadn't seen the exact same stuff.
Yeah, it's like they were all developing their own unique style, but they were all tapping into some, like, fundamental truth about how faces work.
Wow. Okay, so that must be where those geometry adaptive harmonic faces come in, right? The
Mhm.
GAHBs. Time to demystify this thing, because now I'm lost. What are these GAHBs and how do they turn AI into like a portrait painting prodigy? Okay, so they're like tuned into the shape of things, but how does that help the AI actually create something new? Like, does it just say, okay, I see how these waves fit this face, now I'm going to go make a new face with the same waves?
It's kind of like that, but way more nuanced. The model figures out which of those GAHBs, those wavy patterns that fit the image's shape, are the most important ones, the ones that really capture what makes a face a face. It's almost like they're finding the essential ingredients, you know?
The bare minimum you need to make it recognizable.
Exactly. And then they can use those essential ingredients to create something totally new, something they haven't seen before.
Okay, so it's not just copying, it's more like understanding the fundamental building blocks.
Yeah, exactly. And
Yeah.
what's wild is that these models seem to be drawn to these GAHBs naturally. It's like they've stumbled upon this really elegant way to understand certain types of images.
So it's like their intuition is leading them to some fundamental truth about how images work. That's kind of cool. But I mean, did the researchers actually prove that, or was it more like, well, it seems like they're using these GAHBs. How did they figure that out?
They got really smart with their testing. They use these special images, cut images they call them, that are like perfect for breaking down into those GAHBs.
Mm-hmm.
Imagine like a picture of a landscape with rolling hills.
Okay, I'm picturing it, lots of smooth curves and stuff.
Exactly, the smooth curves, those gradual changes. That's like GAHB heaven. That kind of image lends itself perfectly to this type of representation.
Ah, okay. So they gave them like the ideal GHB material, and then what? Did the AI pass the test?
Oh yeah, they aced it. And here's the kicker. They didn't just create, like, decent copies. They were coming up with representations that were eerily close to what's known as the bandlit basis.
The what now?
The bandlit basis. Don't worry too much about the name. Just know that, mathematically speaking, it's like the gold standard for representing images like those comp pictures.
So you're saying these AI models, just by doing their thing, stumbled onto a solution that mathematicians had already proven was like the most elegant one? That's wild.
It really is. It shows that they're not just like randomly messing around. They're actually uncovering some really deep truths about how images work. But of course, the researchers didn't stop there. They wanted to know what happens when you challenge these GHB-loving models with something a little different.
Okay, yeah, because the world isn't all rolling hills and smooth curves. So what did they throw at them?
This time, they went in the opposite direction. They ditched the complexity of faces and landscapes and gave the models something much simpler. Data sets of disks. Just plain old disks.
Discs. Really? How hard can that be?
You'd think it'd be a piece of cake, right?
Mm-hmm.
But here's the thing about disks.
That's a catch.
The best way to describe a disk, to represent it, isn't really about its curves or textures or anything like that. It's more about its spatial transformations.
Spatial transformations.
Yeah, like, think about how you describe a disk to someone. You wouldn't talk about its, like, texture or its shading, would you?
No, I guess I'd say like how big it is, where it's located, that kind of thing.
Exactly. It's all about its size, its position, its orientation. It's about where it sits in space, not so much about those wavy GAHB patterns.
Ah, okay. So for disks, the language of description is different. So how did our GHB-loving AI models handle this change of scenery?
Well, they didn't totally bomb, but let's just say they weren't exactly in their element. They could still create the disks, don't get me wrong, but their performance wasn't as impressive. It was almost like they were trying to fit square pegs into round holes, still relying on those GAHBs, even though they weren't the ideal tool for the job.
So even though they're capable of learning and generalizing, they still have these kind of like ingrained biases, like a favorite tool they keep reaching for, even when something else might work better.
Yeah, that's a great way to put it.
Mm.
And it makes you wonder, if those GAHBs are like their favorite tool, is there a way to give them a more diverse toolkit? can we help them be more adaptable?
So how do you give an AI a more diverse toolkit? Like, how do you teach it to use a different brush, so to speak?
Well, it all goes back to the data, right? If they're only ever exposed to certain types of images, it's kind of natural that they'd lean on those GAHDs. It's like, think about those art students again. If they've only ever studied portraits, they might struggle when they try to paint a landscape for the first time.
Right. Got to switch up the subject matter a bit.
Exactly. So by training these models on more diverse data sets that include a wider range of images, we can help them develop a more well-rounded, visual vocabulary, like give them that bigger toolbox, more brushes to choose from.
Makes sense. More visual experiences to learn from. But even with all the right tools, don't you still need to know how to use them? Like, can you actually change the way these models learn, make them less reliant on those GAHBs when they're not the best fit?
Now that is the million-dollar question.
Yeah.
And researchers are like all over this right now. There are some really cool approaches out there. One that's showing a lot of promise is called adversarial training.
Okay, adversarial training, what's that?
So picture this.
Yeah.
You have two AI models, right?
Okay.
And they're like pitted against each other.
Like a face-off.
Exactly. One model is trying to generate images, do its AI artist thing, while the other one's trying to spot the fakes.
Oh, so it's like a game of AI chess.
Yeah.
Each side trying to outsmart the other.
Exactly. It's this constant back and forth. And what happens is that model that's trying to create the images, it's forced to get more and more sophisticated, more creative to fool the other model.
Ah, so it has to learn to break its own rules, in a way.
In a way, yeah.
Oh.
And that can help them break free of those GHB biases and find totally new ways of representing what they're seeing.
Wow, that's fascinating. So it's not just about the data itself, it's about how you structure the learning process.
Exactly. The more we understand how these models think, the more creative we can get with how we teach them.
It's like we're all students here, learning as we go.
Well, we've covered a lot of ground today, from the nitty-gritty of GAHBs to, like, the future of AI art itself. What's your big takeaway from all of this? For me, it's just this reminder that even though these AI models can do incredible things, they're still just that, models. They have their quirks, their biases, just like us.
And knowing how they work, like really understanding that, is crucial if we want to use them responsibly.
Right, exactly. And to keep pushing the boundaries of what's possible.
Absolutely. And for you listening, here's a little something to think about. As you're scrolling through your feed and you see those amazing AI creations, ask yourself, how would you push those creative boundaries even further? What kind of AI artist would you create? Until next time, keep those brain gears turning.
Okay, so you've seen what those AI image generators can do, right? You type in something wild like astronaut riding a unicorn on Mars and boom, there it is. It's honestly mind-blowing.
It really does feel like magic sometimes.
Right.
Yeah.
But what really fascinates me is how these AI models, specifically these diffusion models, actually learn to create those images. I mean, they're trained on a massive amount of data, but still, how do they generate something they've never seen before? How do they not just become a copy-paste machine of their training data?
That's the million-dollar question, and the answer lies in how these diffusion models work. They don't simply memorize images, they learn the underlying structure and patterns, kind of like deciphering the fundamental building blocks of an image.
So instead of memorizing a specific picture of a cat, it's more like they learn what makes a cat, the shape of the ears, the texture of the fur, those sorts of things.
Exactly. It's like they're learning the essence of catness, rather than just memorizing a million different snapshots of cats.
Okay, that makes sense, but how do they actually do that?
Well, the key is in understanding how these models function as denoisers. Imagine you have a photo that's completely covered in static, like an old TV with bad reception. The denoiser's job is to slowly remove that static bit by bit until a clear picture emerges.
So it's like taking a super blurry photo and magically sharpening it until it's crystal clear.
Precisely. And the fascinating thing is, by studying how these denoisers work, the researchers in this paper uncovered a surprising secret. They found that the AI effectively creates a specialized toolkit for each image, but instead of screwdrivers and wrenches, these tools are mathematical constructs called geometry adaptive harmonic bases.
Geometry adaptive harmonic bases. Okay, you're going to have to break that one down for me. I'm picturing something like musical notes, but for shapes.
That's a pretty good way to think about it. Imagine you're an artist, but instead of brushes and paints, you have this set of magical tools. These tools can create waves and ripples of different sizes and shapes that adapt to whatever you're drawing. So if you're drawing a smooth curve, the tool morphs to match that curve. If you're drawing a sharp corner, the tool adapts to create that sharp angle. These shape-shifting tools are basically the geometry-adaptive harmonic bases.
Okay, so instead of a one-size-fits-all brush, it's like having a brush that automatically changes shape to match whatever you're painting. That would make painting something super intricate, like a butterfly wing, a lot easier.
Exactly, and what the researchers found is that these AI denoisers, as they're learning to remove noise from images, they're basically figuring out the optimal set of these geometry adaptive tools for each image. They're essentially learning to see the image in a fundamentally different way than we do, picking out the most important features and using these special tools to recreate them.
Wow, so it's like these tools are giving the AI a superpower, the ability to perceive and understand the underlying structure of images in a way that we, with our limited human senses, might not ever fully grasp. That's kind of mind-blowing, but how do we know these geometry adaptive harmonic bases are actually doing what we think they're doing? Did the researchers put them to the test?
Oh, they definitely did. They created these special images with really well-defined contours and textures, almost like exaggerated line drawings. And they found that the AI consistently learned to use these geometry adaptive tools to recreate these images with almost perfect accuracy.
So, like, it's really figuring that out on its own.
Yeah, it was like watching the AI uncover a hidden blueprint within the images and then use that blueprint to reconstruct them flawlessly.
So it's like the AI is learning the secret language of images, this hidden code based on geometry and harmonics, and it's using that code to not just copy, but actually understand and generate completely new visuals.
Precisely. It's as if these models are revealing a fundamental truth about the way images are structured. A truth that has perhaps always been there right under our noses, but one that we, with our human perception, haven't been equipped to fully grasp.
That is so cool. But it also makes me wonder, are these geometry adaptive harmonic bases always the best tool for the job? Or are there times when the AI might need to switch tactics? Like what happens when you throw images at it where these tools aren't the perfect fit?
That's a brilliant question, and it gets to the heart of how these models learn and generalize. The researchers tested this by training the AI on a data set of incredibly simple images, just basic disks of different sizes and positions. Now these images are so simple that we actually know the mathematically optimal way to remove noise and generate them, and it doesn't involve these complex geometry adaptive harmonic bases. You'd think the AI would catch on and adopt a simpler approach, right?
Yeah, like why use a fancy multi-tool when a simple hammer will do the trick?
Exactly. But here's where things get really interesting. Instead of switching tactics, the AI clung to its preferred set of tools. It was almost as if it had become so accustomed to using these geometry adaptive harmonic bases that it couldn't help but apply them even when they weren't the most efficient approach.
So even though it could have taken a shortcut, the AI was so convinced that these tools were the key to understanding images that it stuck with them, even if it meant making things a bit more complicated than they needed to be.
It's like the AI had developed a sort of artistic preference for using these tools. Like giving a master sculptor a set of chisels, they're going to naturally gravitate towards using them, even if you hand them a lump of clay that's better suited for molding by hand.
So it's like this inherent bias baked into the way these AI models learn. It makes me wonder if these models are so drawn to these geometry adaptive harmonic bases. Could it be that there's something inherently harmonic about the way images are structured in the first place? Maybe we're just seeing the world through geometry-tinted glasses all along and never realized it.
Now you're really hitting on something profound. It's as if the AI is holding up a mirror to our own visual system, revealing hidden patterns and biases in the way we perceive the world. But the exploration doesn't stop there. The researchers took this a step further and asked, what happens if you completely disrupt the structure of these harmonic bases? Imagine taking those beautifully organized tools and just scrambling them up, like mixing up all the pieces of a puzzle.
Okay, now you've got me really curious. How do you even go about scrambling something as abstract as a harmonic base?
Well, in this case, they did it by taking images of faces and just shuffling the pixels around randomly. Imagine taking a beautiful portrait and putting it through a blender, pixels scattered all over the place. Then they fed these scrambled images to the AI and observed how it tried to make sense of the chaos.
So they basically hit the AI with a visual earthquake, scrambling all the familiar landmarks.
Precisely, and even then, faced with this chaotic jumble of pixels, the AI still tried to use its beloved geometry-adaptive harmonic bases. It's like it was so convinced that these tools were the key to unlocking the secrets of images that it couldn't even conceive of another way to approach the problem.
It's like trying to fit square blocks into round holes. It just doesn't compute.
Exactly, and the results were pretty telling because the pixel relationships were completely out of whack. The harmonic bases couldn't do their job. The AI's ability to remove noise and generate coherent images plummeted. It was like watching a master chef trying to bake a cake with all the ingredients mixed up, the tools and the talent were there, but the fundamental structure was missing.
It really highlights just how important this underlying structure, this harmony within images actually is. We take it for granted because our brains are wired to perceive it effortlessly, but for AI, it's a whole new world of understanding.
And the crazy thing is this research focused specifically on AI image generators, but who's to say these geometry adaptive harmonic bases aren't playing a role in how AI learns to understand and generate other types of data?
You mean like music or language? Are there hidden harmonic structures in the way melodies are composed or in how we string words together to form sentences?
It's a tantalizing thought, isn't it? It's like AI is uncovering these hidden codes, these fundamental building blocks of information that extend far beyond the specific tasks we train them on.
It's almost as if we've stumbled upon a new Rosetta Stone, a key to understanding not just how AI learns, but potentially something even deeper about the structure of information itself.
Yeah.
It's exciting and a little bit humbling all at the same time.
Exactly. And the most exciting part is that we're just at the very beginning of this journey. As we continue to develop more sophisticated AI models and delve deeper into their inner workings, who knows what other hidden patterns and structures we might uncover?
This entire deep dive has been a mind-bending journey. It's made me realize just how much we take our own perception for granted and how much more there is to learn about the world around us, maybe even about ourselves, through the lens of AI.
Absolutely. And for anyone listening who's eager to delve deeper into this fascinating world, we've included a link to the full research paper and even the code they used in the show notes. Don't be afraid to get your hands dirty and explore. You never know what insights you might stumble upon.
That's right. Happy deep diving, everyone.